Hello everyone, and thank you for joining us today in the first of our application webinar series. We're going to be talking today about thermoforming using 3D printed molds. Our speakers today are Alex Benham. Alex is an application development specialist at 3D Systems, so he works on a variety of different uses of 3D printing technology and sort of fleshing out and making sure that one or more of our print technologies will work well for a given application. And so he's going to be talking to you today about thermoforming and giving you the technical background. In addition, myself, Tom Sharon, will be sort of emceeing today's webinar, and I'm the VP of Product Marketing at 3D Systems. So I want to talk a little bit about who 3D Systems is very briefly. For those of you that are not familiar with us, we're a public company based in Rock Hill, South Carolina, and we make the ideal real. We're both the originator of 3D printing and the shaper of the future of 3D solutions, and we really pride ourselves on making those solutions accessible, simple, productive, and gratifying to use so that you can transform your ideas into tangible outcomes. As many of you know, 3D Systems has by far the broadest portfolio of 3D printers and 3D print technologies in the world. And we have printers really that range from sub $1,000 systems like the Cube that you see in the upper left-hand side, which are great for your home, in the living room or in the classroom or your garage, all the way up to systems that cost in excess of $1 million. And these are production-level systems that can print in metal in a variety of different alloys, such as aluminum, titanium, stainless steel, and so forth, to highly productive plastic 3D printers that make tough end-use parts, and a variety of systems in between that can make full color parts, functional prototypes, concept models, so on and so forth. There's really a breathtaking array of capability and things that you can print on different 3D Systems printers. And when we're talking about the applications of 3D printing, we can broadly categorize them into one of 5 categories. Starting from the left-hand side, concept models are really all about communication. And so it's all about communicating your ideas before you've committed to actually manufacturing something or building something. So we have architects using printers to print examples of, as you see, a bridge or buildings, and sell a concept before it's ever materialized, or to sell an engineering idea, variety of different things. And this is really about the aesthetics and being able to hold something in your hand and really truly understand it. Then there's functional prototypes, and this is all about validating your design and engineering concepts. So this is, the goal here is to create parts that approximate the end-use manufactured parts, but they're still prototypes, so that you can actually test your parts and validate ideas. In the middle we have tooling, and that's what we're going to be talking about today with thermoforming. This revolves around pre-production and even into production level tooling. In fact, in the case of thermoforming, it is production level tooling that can be printed. And the goal here is all about speed and being able to create tooling in a much shorter amount of time, often more economically than using CNC or other methods to make tooling. And especially when we're talking about short-run production, there's massive value in being able to 3D print your tooling and go through pre-production and into production. Of course, we can make end-use parts in metal, in nylon, in other types of plastics. We have a variety of companies around the world that are 3D printing end-use parts every day. And in fact, there's a lot of 3D printed parts that fly in aircraft, including the Joint Strike Fighter in the United States. And the last category is really about healthcare, and that's mass customization. So when you want to print millions of individualized pieces that fit an individual patient or an individual customer, 3D printing does an amazing job at that. And with that, I'm going to hand it over to Alex so that we can jump into the thermoforming agenda here. Alex?
Yes, thank you, Tom. Can you hear me?
Yes.
Checking? Okay, fantastic. Good morning, everybody, or evening, depending on where you are. Before we get into the thermoforming and everything, I want to kind of run you through the agenda of what we will be looking at today. So first of all, we're going to be looking at what is thermoforming. Hopefully most of you know it, but we'll briefly cover it. Then we'll cover some traditional methods of thermoforming, and then we'll really get into how the 3D printers affect thermoforming, you know, what printers we're recommending for this process, and how we do the process in terms of printing and actually thermoforming as well. Then we'll talk about more how 3D systems can help and some real-world examples of thermoforming to kind of get your brains and on all your gears in your brains thinking about what we can do with this. Yeah, there we go. Okay. So for thermoforming, if you don't already know, it's a process for forming very thin sheets of plastic into some type of shape. It's very, very common in packaging and things of that nature for putting a shape around a part, a desired part. Vacuum forming is an extremely common type of thermoforming, which uses a negative pressure to pull the plastic down around the mold and uses heat as well to make the plastic malleable enough to form around whatever your mold is and create the end part. Typically for thermoforming, most of the tools that I've ever seen are milled out of metal, things like steel or aluminum. More commonly aluminum, it's just a little easier to mill and to work with. But you can also make it out of a lot of other things like wood, sometimes clay even, and there's a lot of different stuff that you can do. But making these molds, especially if you're going to make multiples of them, can be very costly, especially if you're trying to make them accurately the same. It can be very costly to make and time-consuming to do as well. Especially if you're modifying, like I mentioned earlier, modifying or to make multiples of the same thing and ensuring that they are the same, in fact, will make the same part. It can be very difficult to do with these processes. Wait, there it goes. Okay, so 3D printing and how it affects thermoforming. So what 3D printing is great for is for making prototype design molds. So if you're in the design process and you're working on your packaging and you're saying, what are we going to do to, carry this part or secure this part in our packaging, 3D printing is a great technology to use because it makes you, or it gives you the ability to modify your design multiple times and make it very quickly. And additionally, when you're prototyping, it can actually be used, once you get to the end prototype design, most of the time you can actually use that mold that you used for prototyping, you can use that in production. Depending on what you want for your desired part, surface finish may become a big factor and can actually be used for your production molds in some of our larger, more higher-end technologies. Additionally, for thermoforming, one kind of pitfall of it is if you ever have pockets or corners that are hard to pull air out of, you sometimes have to go in secondhand and use a drill or some sort of CNC to drill out a vent hole to get the air place to go. With 3D printing, there's two benefits really. Some of our materials are actually porous, so they will allow the air to flow through them so you don't have to make any vents. Or the second ability is that you can easily design in vent holes and just print them straight into your mold and not have to worry about going in by hand and drilling out any vent holes. It kind of prevents any human interaction error. So just like the webinar says, there's 5 easy steps to do this. And so right now we'll go through them really quick to explain to you what you need to do to be able to do this. The first step is to make your mold. So for our webinar today, we're going to be focusing on our prosumer and professional line of products. Technically any of our printers can do it, but we weren't really focusing on our giant production systems, so we're focusing on our PJP, our Cubes and our Cube Pros, CJP, color jet printing, the X60 series, or the 4500 even, MJP, so we're looking at multi-jet printing with 3500 or the 5500, even 5000, and then SLA, which is stereolithography, and that would cover the 6 and 7000 in our professional line. So the first step is just make your mold. And now the second step kind of falls in with the general line of thermoforming and how it's regularly done, is to prepare the mold. So that may include, depending on what technology you use, you may need to finish the mold, give it a better surface finish, just make it look cleaner, or preheating the mold before you actually do the thermoforming on it. And then also just positioning it, orienting it, mounting it to a plate to do thermoforming on. Third step is to prepare your plastic sheet for forming. You can use any kind of sheet, any sort of plastic sheet. There's tons of different materials you can use, different sizes. And basically what you do here is to clamp it into your machine and heat it up to its so it's malleable enough to form around your part. Fourth step will be to actually form the part. So here you can see, applying the plastic sheet to the molds and then actually using the vacuum to suck out any additional air that is trapped to form it to the shape that we want. The fifth and final step is to remove your mold and finish the part. So here we just simply remove the mold, but in a larger production environment or in your prototyping environment, you're probably going to need to cut around the excess, any excess plastic left on the mold. You want to cut it out. But for us, we just removed them to look at the results and see how it came out. And that's really it for how we do the process. But now to get more into the deeper in portion and the technical part of what machines we're going to be using, why they work, some tips and tricks for the design process, and so on with our solutions. So first and foremost, what print engines are we using? So print engines are technologies that we have. What I mentioned earlier, PJP, plastic jet printing, CJP, color jet printing, MJP, which is multi-jet printing, and SLA, which is stereolithography. So to choose one of these technologies, there's a few factors that you might need to look into to figure out what technology is right for you, right for your application. So right here we have mold longevity. How long do we expect this mold to last? How long do we expect, or how many parts do we expect to get off of this mold? Surface finish. What kind of quality part do you expect to get off your mold? Do you want it to look very nice and shiny, a little bit rougher? What are you going to be using in production? Things like that. Accuracy and feature details. Thermoforming as a whole, you don't really have a whole lot of feature details, not a lot of fine features, but it definitely impacts it when you're designing it for printing. What your machines can do and how they will affect the end part. Minimum part size also falls in with feature detail and accuracy. Is kind of what are the limitations of the machine. Additional uses of the printer. Each printer, depending on what you have, will be able to do much more than just building thermoforming molds. You can do a whole lot of stuff with them. So it's really, what are you going to do other than thermoforming? And then, finally, some more machine-based things. What is the size of your anticipated printing? So if you're making really big thermoforming molds, you're going to need a bigger machine, and maybe the Cube or Cube Pro won't fit you. But if you're doing really small parts, maybe the Cube or Cube Pro will. And then so on with the cost of the printers as well. You know, if you have a very large budget and you are going to be making bigger parts, you can go with a bigger machine. Or if you don't have the budget, you can go with a smaller machine. Exactly. So again, I just wanted to reiterate our technologies here. We have, for this thermoforming application, we are recommending plastic jet printing, color jet printing, multi-jet printing, and stereolithography. Additionally, SLS, selective laser sintering, and DMP, which is direct metal printing, they can be done, but we're focusing on our professional machines and our prosumer machines. Okay, so now into our materials that we have. Like I mentioned before when we were talking about venting, some of our materials are actually porous, and that's really awesome for thermoforming because it allows you to get really good pull, especially if you're doing vacuum forming. It allows you to get very, very good pull onto the plastic and get it down into your corners so you can get better features and not rounded out edges. You can get those sharper corners. And additionally, if you don't have the porous materials, you can also design in the venting. Now, for the materials that are porous, that includes our PJP and our CJP materials. Basically, these things, they are porous in nature. They do allow air to be sucked through them, and it basically prevents you from needing venting. You don't need any design changes afterwards. You don't have to go in by hand and drill holes. You don't have to design them into your part. It doesn't trap any air, and it gets very good pull through the part, through the porousness nature of the part, to pull down any trapped air that you have stuck in the forming process. MJP and SLA, on the other hand, based on the way that they are actually formulated and the machines work, they are not porous, but they do offer a higher surface finish, and that's kind of a trade-off that they have. But with these machines, MJP and SLA, which are highly accurate, it's very, very easy to design in very small vent holes. They can, like we mentioned earlier, pull the air out of pockets or corners. And you know, if you forget to design them in, it's not that hard to just drill them out by hand either, like a traditional way. But I mean, for me, I would always recommend designing them in so you can get them exactly how you like them. Now for surface finish. Our materials, they kind of fall into two categories, coarse and smooth. Obviously, the coarse here is a little bit exaggerated to show you the difference, but you know, some of our materials are a little rougher compared to some of our other ones which are smoother, and that will transfer through to your form part depending on how thick it is. So you know, if you have a very, very thin piece of plastic, for example, in our example here, we used a 20 thousandths thick, so 0.02 inch thick piece of plastic, and that size will transfer the surface finish through. But once you get larger, you will actually notice that surface finish won't actually affect it that much. So which ones are which? PJP and CJP, if you've ever worked with them, they have a rough nature to them. You know, with PJP, the layer lines and the draw lines are very apparent. Even with reduced layer thicknesses, you can still see them. On CJP, the material itself is a powder, so the part that comes out of it is kind of granular in texture and kind of gives you a rough-looking finish. But even that being said, it's not necessarily a terrible thing. Sometimes you may be designing a rugged-looking piece, or maybe an industrial piece. For example, something that may go in a toolbox, maybe. You know, and you want that to look rugged and look like it can withstand a lot of beating up. You know, maybe these surface finishes are something that you actually want. So it's not necessarily a bad thing. And even if you don't like it, there's always a lot of finishing techniques, such as sanding, that can be used to reduce the surface finish and make it much smoother and more desirable to a nice shiny finish. Now, the MJP and SLA, they, like I mentioned earlier, because of the materials they use and the process involved, they are a much, much smoother surface finish. So they will actually can be used for production molds without any changes or final finishing of the part. But again, that also depends on what you want your final part to be. So if you want it to be shiny, MJP and SLA. If you want it to be a little rougher, PJP and CJP. And exactly. So now for some design and build recommendations. You know, molds in general are usually very big, bulky parts, and will usually use up a lot of material depending on what they are because they're so big and bulky. And just like a lot of other things, we have the ability to hollow a part out or add ribs into it to reduce material usage. It saves on costs, makes the part much lighter and easier to handle as well. So there's not really a big issue. You can design your mold to be hollow. You can also add ribs in it for support. And if you find it necessary and you need a little bit extra support, you can backfill it with some sort of foam, like expanding foam, and just cut it flat, and that'll make the mold solid, but very light. And then kind of just to recap everything about PJP, CJP, MJP, and SLA, these are just one-liners to help you get a better part for thermoforming depending on what you're looking for. So for plastic jet printing, we're going to want to set up our builds for cosmetic layer lines. So basically what I'm saying is in a way that will make the layer lines least apparent. For CJP, again, you can easily sand the part. It's very easy to sand. Just grab some 220 or 400 sandpaper and just polish off the surfaces, and you can get a much smoother surface finish if that's what you desire. MJP and SLA, the only real change here that we might need to implement is designing in vent holes. And again, it's super easy to do in your design software. Just drill them straight through the bottom. And now to kind of help you choose a machine that would kind of best fit your application, we have this table here with values on each technology versus parameters that might be affecting your choosing of a machine. And these values are actually based on the molds that we showed earlier that we did on our vacuum forming process. So in terms of printing, surface quality, and part cost, it might fluctuate depending on what your part is, but this is a pretty good general guideline. I'll let you guys, look through this later on if you would, or if you haven't already. And hopefully you guys, if you've seen these machines before, might already have an idea of what these values are meaning and how they relate to one another. Now again, just to recap, the machines that we are recommending for this process, again in our prosumer and our professional series, we have our PJP line, which is plastic jet printing. For our part that we used a Q Pro. For CJP, which is color jet printing, we have the X60 series. We specifically used a ProJet 660. We have MJP, multi-jet printing, with 3500s, 5500 and 5000. Specifically, we used a ProJet 3500 HD Max for WAR testing. Then we have SLA, stereolithography, which includes, the 6 and 7000, the 800, and the 950. Specifically, we used a ProJet 6000 for our testing as well. So now I want to kind of get you guys thinking about, maybe we haven't done thermoforming already, maybe you already do thermoforming, but I kind of want you thinking of what can we do with thermoforming? What are some standard things that are built around the world with thermoforming? And some very easy ones, which I mentioned earlier, packaging. You can either use it for packaging very delicate things from eggs all the way up to mechanical stuff like bearings and shims and all that stuff. You can literally package probably anything with it, and it's probably the most common industry that actually uses vacuum forming and thermoforming but there's a lot of other ones. So for example, we have tableware. So I'm sure a lot of people have seen the solo cups before, the little red cups or solo plates that you take out to, a little picnic. And of course, takeout trays, which are used all over the place. Those are all very, very common thermally formed objects. Now, getting into some more interesting ones. One of my favorites actually is candy molds. So a lot of places that make fancy chocolates will actually use thermoform molds to pour chocolate into them to get the really interesting shapes you might see in a chocolate box. You can also use them for lollipops or suckers, whatever you call them, and a ton of other candy is formed using these molds that are made from thermoforming. Then we have signage, like the big signs you ever see on restaurants or drive-throughs. Obviously, we got Taco Bell, and they have all these signs that they have that are lit up, thermoformed. And then they also have, other signage like a taxi light on top of a taxi car. That's another thermoformed object. And there's a whole bunch of other things that you could, point to that would be thermoformed signage. Some more interesting ones, body panels. So here, this is a very small one. This little race car here is a remote control car, but the body panel for that would be thermoformed. Even possibly body panels for larger race cars could be thermoformed, and they might be. I'm not 100% sure, but then we also have some larger panels that would be used on John Deere tractors, some bigger, bulkier parts that would be used for thermoform. And then here's another interesting one: is tanks that can be filled, either plastic gas tanks that will be used for either twin thermoforming, where you actually form an entire sheet together and then fold it on top of itself to make a closed tank. It's a very interesting way to do it as well. And then one of our biggest customers that hopefully some of you haven't heard about is Align. And Align, if you don't know, makes Invisalign braces, which are thermoformed sheets of plastic you used to, or in place of the metal braces. And Thermoform is actually one of our customers, and they use our SLA machines to print over 17 million parts a year that are then thermoformed to make these braces to help people have nice straight teeth. And now I want to get into 3D Systems as a whole is a full solutions provider. We don't just do 3D printing. We have 3D scanning, we have designing software, machining software, obviously 3D printing, and then we have some inspection software with scanners, and we also have haptics. But another large impact that we have in thermoforming is our design software. And here we have, like I mentioned earlier, we have a lot of design software. We do a lot of different stuff. We do mechanical design, some freeform design, and then for this one, mold and die design, which is very, very important to thermoforming in any kind of mold or industrial application. So specifically, I want to talk about Cimatron and very quickly go through an example that we have done with Cimatron to actually create mold and dies that were used for thermoforming. So we had a customer that came to us with this part seen here, and this is the final piece that they wanted. So they came to us and said, we want to thermoform and get this as the end result. You can see the specs that we needed on what material and the size of it. So our guys over at Cimatron, which is our design software company that makes mold and tools, is, they were like, all right, let's do this. So they took this design here, and they went and created a mold of it. So for the mold, basically they have to take the inside of it and extend it out to make some runouts, and then flatten it out to a platform that can be, hooked up to a table. So here on the right, you can actually see the finished product. It's a little grainy. The picture's not great, but you can still see it there. So this is something we've actually done with our software to make a real-life thermoform part for customers. Here you can see what the software at Cimatron can, some more stuff that it can do. On the left It actually can show you what the finished thermoform part will look like, and it can also show you where to cut the part to make it. So once you thermoform something, you obviously have some additional run out to extend past the part that you desire. This will be cut off later, and here you can see with the red line, it tells you this is where you need to cut it to get to the part that you desired initially. And here on the right, you can see the finished thermoform part before it is cut away to be the final desired part. And again, using our Cimatron software, we were able to take it from an initial idea that the customer had to say, we want this piece. We were able to design the mold for it and then have it thermoformed using all of our design software and all the solutions that 3D Systems can offer. Additionally, for Cimatron, it can actually, basically what I'm trying to say is it does a lot of stuff. It doesn't only do 3D printing molds or make 3D printing files. Cimatron obviously will make the mold files and design them. It can also generate toolpaths, so if you do want to make a CNC mill and then mill it out of anything that we mentioned earlier, aluminum, steel, wood, or any of that, it can actually do that as well. And not only create a 3D printed piece, it can do a lot of different stuff and make your and produce a full solution for you or your customers about how do we make these thermoform parts. We have the design we want. How do we get to the finished product? And that's what Cimatron is used for. With that, I'm going to hand it over to Tom to finish this up.
Great. Thank you so much, Alex. So now we're on to the Q&A session. So we're going to open it up to questions. And the way that this works is because of the number of people that are on the webinar, we don't actually open up the phone lines. We just have you type your questions into the questions box in the GoToWebinar window. And then we'll go through and answer as many of those as we can for the next 15 or 20 minutes that we have remaining. So I see that a good number of questions have already come in. If you give me just a moment, I'm going to go back and pull out some of these that were asked during the presentation and let Alex answer those. And of course, continue to type your questions in and we'll continue to answer them. One question that was not answered in the slides is one individual says that CJP, the color jet printing, needs infiltration, which from my point of view seals the surface completely. So is there really any breathability?
It's a great question. While yes, we do use infiltration to seal our parts and make them much stronger, it really depends on how you do it, on how much it will seal the porosity. And in fact, I actually know of some customers that don't infiltrate their parts. They're thermoforming, 1 or 2 sample pieces, and being that the thermoform parts aren't very delicate features, sometimes they don't actually even infiltrate at all. And they'll just thermoform right on a green piece, meaning not infiltrated. Not necessarily the most recommended way to do it. Specifically, the way we did it in our example in the webinar that I went over, we did infiltrate our part, but we didn't do it a lot. So we just very quickly dipped it in the infiltration to just coat the outside surface real quick. And basically what that does is just a small amount of infiltration bleeds out through the entire part. And because it's not fully infiltrated, it actually does leave a bit of porosity. But it's a very good question. Infiltration, if you do a full infiltration under a vacuum or in a pressure pot, it will eliminate porosity.
Great, thank you, Alex. So another question is, how large should one make the designed-in holes?
Great question. So I would recommend for MJP and SLA somewhere around probably, sorry, I'm doing a finger measurement right now. Something like 10 thousandths maybe would probably be the minimum that I would try to go. I'd say anywhere between 10 thousandths to 20 thousandths would probably be an acceptable size. But again,
So
that's the minimum.
that's a 1/4 millimeter to a 1/2 millimeter, right, Alex?
Sounds about yes, sounds about right. I'd say anywhere around a millimeter would be the maximum that I would go, but it's really up to you. I'd say in millimeters, I would say somewhere between 1/2 millimeter to a millimeter.
And the follow-up question to that is the other end of the spectrum. What's the smallest diameter hole that the printers can print? And I'm sure that's dependent on which technology we're talking about.
Yeah, it's very dependent on which technology you have. I don't know those numbers off the top of my head about what's the smallest hole, but I know they can make really, really small holes. But if I was doing it, I wouldn't go much smaller than, 1/2 millimeter. That's probably as small as I would go. Because it also kind of depends on what the thermoform part you're trying to make is and how thick that plastic you're forming is. If you have a very thin piece of plastic, it might matter, but if you have thicker sheets, it's not going to affect it very much, no matter how small or how big it is. Basically what I'm saying is the plastic won't get sucked down in that hole if it's too thick.
And another question is, what type of vacuum forming system are you showing in your slides?
I don't know the exact machine name, but I know it was a Formtech or Formec machine. I don't remember the exact model number.
But I believe in terms of this process, using a printed mold versus a milled or machined mold, what equipment you're actually using it on is no different. Is that correct?
Correct.
Good. Another question is, how do you prevent heat from destroying the mold?
So, again, that kind of depends on what you're forming and how thick those parts are, or what you do to the mold before you, basically I believe it was the second step, is prepping the mold. So the way we've done it, and that I've seen from all the experimentation I've done, most of what I've done, we actually don't apply much heat to the mold at all. It's only the heat that's contained inside the plastic that transfers at all to the mold. And even that plastic, it cools down very quickly once you form it. So from everything I have seen little to no heat transfer into the molds. If you were doing a heated mold for preparation, which a lot of people sometimes do to get better results, it kind of depends on what you're doing. Basically, I would limit the amount of heat applied. So I remember I read through and I saw another question about what is the maximum temperature that can be applied. And again, it's very dependent on what technology you're using. Off the top of my head, I would say somewhere around 75 Celsius is usually what I heat treat any parts at, for other processes, not necessarily for thermoforming, and that's usually a temperature that we go up to. So I would say not go too much higher than that, otherwise you might see more deformation. And again, it's very dependent on heat transfer and thermal equations and what the mold is and how big and blocky it is. So keep that in mind too.
Yeah, I think, Alex, can you talk a little bit about how printed molds are also being used for injection molding, and how the heat transfer there ends up that the survivability of the molds can go well above their maximum temperatures, in terms of what you're injecting, just because of heat transfer or lack.
Yeah, absolutely. So just briefly to talk about injection molding, it's not the point of this webinar, but so we have done injection molding on some of these tools before, and on quite a wide range of our machines actually. And for injection molding, we have substantially high temperatures. The highest temperature that I've ever recorded injection molding was 675 degrees Fahrenheit, and we were actually good from what we did. We had 50 good parts off of that at that temperature, and so basically what happens is our materials that we are injecting on, even in thermoforming on, which was mostly the 3500 and SLA machines, they are actually insulators. So basically what that means is they don't absorb heat very quickly. So when you're thermoforming on them or injecting on them, you do put a lot of heat into them and put it on the surface, but you don't do it for an extremely long, extended amount of time. So basically what that means is while heat does transfer and get into the mold, it only does it on the very, very surface of the mold. It doesn't penetrate deeply in, and it doesn't transfer as much heat as it, basically it's saying, well, I said earlier, we have 675 Fahrenheit. After we open up the mold, you can actually touch the mold, and it's not really that hot. To your fingers, it's warm, it's not going to burn you, but the materials themselves are insulators, meaning they don't absorb a lot of heat, and they don't absorb a lot of heat quickly, which is the very much bigger factor, is because you don't apply this heat for very, very long extended periods of time. Sometimes you might, but generally you don't.
Great, thank you. Here's another good question. Can you sell products made with 3D printed molds in every market, such as healthcare, food, etc.? Is there any harm to the human body?
Honestly, I'm not 100% sure. My opinion, or what you should do, is get it checked and have it certified that it's okay to be used in healthcare industries. But we do have some materials that are Class 6 certifiable, and if you are going to do that, I would recommend that you go with those materials. That would give you the biggest chance of making sure you pass those certifications. But I do know for a fact, and I have seen customers, like I was talking about candy molds, they were making chocolates for the tops of cookies, and they were actually thermoforming on a CJP mold, creating these molds for chocolate. I don't know how far they went down their, classification process and making sure it was certified, but I do know that it has been done. So again, just to recap, make sure you get it certified, and I would recommend using our Class 6 certifiable materials.
And those materials are available both on our MJP technology and SLA.
Yes. I don't remember exactly what they are, but it is up on 3ds Central where you can find them.
We have a question here. What about using the Project 4500 plastic color printer? Is that a viable option?
Yes, you can use it. From what I know about the materials in the 4500, so first of all, we have not tried it. We have not actually done it. But you can do it. There's nothing stopping you from doing it. But to keep in mind, basically what I'm trying to say is the porousness of CJP does not transfer to the 4500. The way that material is formulated and the way the process works, it actually makes the part watertight, so it's not porous. So if you are going to do that, you will have to figure out a way to put some vents in there, or just design them in, obviously. But yes, there's nothing stopping you from using the 4500. It can be done. Yes.
Another question here. What is the maximum 3D printer dimension? So I think he's referring to the max size part that you can print.
So it depends on what technology you have. The largest printer that exists that can be done is the ProX 950, which is an SLA machine. I know the rough dimensions. I don't know them exactly. It's about 6 feet by 3 feet by 2 feet, or maybe 2.5 deep. But more or less, beyond that, then you're going to step down to the 850, which is half that size. Then from there, you probably have the 860, which is a CJP machine. That has a build volume of about 20 by 15 by 8. But even
And
though
that's in
you may be
inches.
limited by size, what's that?
Just clarifying, that's 20 inches maximum dimension on the Project
Yes,
860.
inches. Yes. Um, yeah. So even though you may be limited by size, there's nothing stopping you from splitting your design in half or thirds, depending on how big it is, and printing it out in sections, and then gluing it or somehow bonding it together. There's a lot of different materials you can get out there to help bond any kind of material that's printed together and make a larger mold from separate printed parts.
Another question is, are you running a webinar on other molds too? Thermoforming is just one case.
By that, I assume they mean, are we going to do, you mean like the injection molding molds? Yes. So there will be some more webinars in this applications webinar series that cover some molds. One of them I know for sure is injection molding.
Okay, good. A fairly similar question. Can 3D printed parts be used for press thermoforming as well? Will they handle the heat and pressure?
Yes. So by press thermoforming, I'm assuming you mean one where there's a core and a cavity that actually forces the plastic into a shape. Yes, you can. Again, I would recommend at that level probably using the MJP machines or an SLA machine. I'd stay away from plastic jet printing, and I'd stay away from CJP. MJP would probably be your best at that area, and it will handle pretty high substantial temperatures, and it shouldn't have a problem with the pressure.
That also goes for hydroforming. We have customers doing that as well.
Yeah.
So there's a lot of questions about how long a mold will last. How many cycles can it run through?
So we've never actually tested a part to the end of its life cycle. From the testing that we did, we saw no degradation in any of the molds. But again, we were forming, fairly thin plastic. When you're getting into, much thicker plastic that needs more heat, you might see some degradation. But from what I can say, you can easily get, from what we've seen in testing, again, we've never tested it to the end of life, anywhere from thousands to tens of thousands of molds, I would expect you could get off, especially off the MJP and XLA machines. CJP might be a little lower, and PJP as well would probably be a little lower. But I would imagine you wouldn't have a problem running it as a production mold.
There's quite a few questions on here about ordering molds and or finished thermoformed parts from 3D Systems. Do we offer that as a service?
I believe we do. So we have a division here called Quick Parts, which, if you remember earlier, I was talking about all of our solutions that we have. I had a little solutions flower that had the 6 little options on there, one of which is manufacturing. And we do have a division called Quick Parts, which is, that's what they specialize in, is you send them a design, you say, hey, I want this part thermoformed. I want this part made in, a variety of other methods. So yes, if you were to contact our Quick Parts division, they should be able to help you out with that.
Yeah, and further to that, if you just go to 3dsystems.com/quickparts, that'll take you directly there, and you can do online quoting if you upload your 3D file directly there. What can be done to prevent webbing of the thermoformed material when being pulled into a deep cavity? This is probably more of a general question, not specific to 3D printed molds.
Yeah. So for webbing, from what I know about webbing, it generally happens when it's going between 2 large male features, and essentially it's when the plastic won't get sucked down all the way and it creates a very sharp edge. I've seen a few different ways to get rid of that, and basically it's excessively heating up the plastic so it's very, very malleable, so almost to its liquid state, and it's very, very soft. That will give it the ability to, it stays hotter longer, which allows it to get pulled deeper. And then there's also, I forget what it's called, but it's basically on, they will try to vacuum form a part, and if it doesn't go down all the way, they'll actually use a blower to blow it back up. So they'll pull it down with negative pressure, and they'll pump some positive pressure in it to pump it up and make a bubble almost, which stretches out the plastic even further, and then apply a vacuum the second time, so applying the second negative pressure and pull it back down very quickly and suck it down into deep draws. That's just some standard thermoforming processes that I know of.
How long does it take to print a mold that is, in this case, 25 inches by 16 inches by 6 inches? So that would be SLA, to print that size of mold as one piece. So 6-inch tall part, Alex. What's your?
So 6 inches. Well, it's not all dependent on the Z height, but let me think. On SLA, to build something that's approximately 6 inches tall, it probably puts you around 15 hours at that size. Being that tall, or being that 25 inches as well, it's going to add a little bit. So I'd safely say 20 hours. That's with a little cushion, just to be safe.
Yep. We have a question here. My interest is in using printed molds for injection molding of plastic and rubber parts. Your cost to print molds is currently much higher than CNC or EDM. Do you see that going down anytime soon? And I think that's a misnomer. I don't think we'd agree with that statement. It's very dependent on geometry, but Alex, can you talk a little bit about, in general, the cost to print a part, let's say on MJP or SLA versus CNC or EDM?
Yeah, absolutely. So just as a quick little tidbit or a little note, this will be covered later on in our injection molding webinar in a few weeks. I'm not sure exactly when that date is, but it will be covered in this application series. But yes, so I understand where you're coming from, and we've actually done a study on this using a few different mold designs. So we found from the molders that were the milling shops that we have been to and asked and quoted, a specific mold that we were using, which is actually our biggest one that we've tested. It was going to take approximately $4,500 US to be milled out of. I don't remember exactly what it was milled out of. I think it was aluminum. Anyways, to print that mold costed $503 US. So it's substantially cheaper to print that mold. That being said, our molds, compared to an aluminum or steel mold, it won't make as many parts maybe, but at the same time, if you need 4 printed molds to get the same quantity that you were expecting out of an aluminum tool, $503 times 4 is $2,012. Compared still to $4,500 is still half the cost. So, you'd have to do some math. Again, like Tom mentioned, it is extremely geometry dependent. It's a single case every single time. It's not a one answer fits all thing. But from what we have tested, our parts were substantially cheaper to build with printing rather than CNC.
All right. Well, we have burned up the entire hour. There are still a lot of great questions that we unfortunately don't have time to get to. For those of you that have asked questions that we didn't answer, We will be responding to you after the webinar. We track the questions, and so we know that you've asked them and that we haven't been able to answer them. We will get connected with you, and I want to thank everybody for their time today. Alex, I want to thank you for both the technical work that you've put in and for taking the time to present all this information for everyone. We hope you found it useful and educational, and we hope everyone has a great day.